Hello, and welcome to the short talk about my project AI on the Edge. Can you unmute yourself then, or mute yourself? Okay. So the project started with a seminar I did. And it used edge devices. This is this little things here called wait a second, Jets Nano. So it's a microcomputer development kit, and actually it's produced by NVIDIA, the graphics card company, now famous for AI. And the cool thing about it, so you can deploy machine learning models on it, and you can use it for classification. And in the seminar, we had the idea and used it on this small scale world here. You see that? And the interesting thing is the system is not able to relate to scale, so it's classifying the voice according to be a person. And what is also quite interesting or important in context of machine learning and classification, that you always get a percentage of classification. So that means there's never 100% certainty of classification, so you get for all available classification classes, you get a percentage, and you can then define the threshold when this value becomes true. So it becomes classified. Can you continue? So, and then I decided to apply for the RT4 at Weimar University here. And I thought about this system. So actually also having a model city and a robot arm that is then also provided with a camera, and build this kind of network structure for then analyzing the videos and so on. So we have a camera array with several cameras, a server structure, a robot arm with our own development kit. And I refer to a system developed by NVIDIA called Deepstream, which I think was really interesting and also a powerful tool. And can you switch? Yeah. So, and this is now the result. Now it's a prototype. So it was announced that it will be shown today, but it is not possible. I will set it up here next week. And I will also use the infrastructure in the room here. And what you see here is this is the Orin device of NVIDIA. These are industrial cameras. We got them from the DBL. It was quite a task to manage that they work. And this is the toy world, and this is the robot arm also with a camera. And you see here the classification. I used a model called YOLO. It's quite fast. And so all the processing and classification, the machine learning tasks are done by this tiny device here. So it's mostly used for machine driving cars and so on. And it's using the Deepstream architecture. So when it runs, it's quite stable. Can you continue? So some examples here again. So it's now that's the prototype still. Can you continue? So, and then you see here, that's the classification windows. So it's handling all the streams at the same time, and you see classification doesn't work not so well in some points, and you see it's also counting. Right? So you can also use it for traffic counting, and I use a specific model I can explain later a bit. So you can use different models and different systems. I use YOLO, which you might know. It's quite fast and quite well known. Can you continue? So, and why I'm really interested in that, or why I'm into that at all, is because I was employed or working with the FMX conference in Stuttgart. And so I don't know if you know it, it's quite a big conference for special effects and animation. So it's probably 4,000, 5,000 people a year. And so we manage the streaming structure and infrastructure. Maybe you can continue. And so we built them a custom-made system. And so the setup of the FMX was that they have several locations inside the Haus der Wirtschaft, which is quite a big venue, like 10 different rooms of different sizes. So, and we want to stream from the large rooms where the big speakers from Sony speak, but also from small rooms. So we got we developed a system with small self-configured devices, computers, with capture cards, small NVIDIA cards on it, and then networking devices. So in all these rooms are then streaming to a central server system. It has the reason that there was quite security problems because of overcrowded rooms. So we were able to build overflow rooms with large screens, so we can reroute the people in there so they can watch it. So we needed a quite flexible system to route and reroute video. And at the center was an HTTP server, so this is also the benefit that we could record stuff. And then for internal purposes, bring that to the Filmakademie Ludwigsburg so that they can relink the web pages to the server and then watch the videos. So it has had several iterations, and at the end we had that, which is also I think quite interesting, because a big problem is we could not see how many people were there. So we needed to install another surveillance system to see how many people are sitting in front of the screens and if the screens are working. And for that, we used a system called iSpy. I don't know if you heard about it. So it's a ready-made system for surveillance, which you basically can open source download, and which brought quite crazy results. So this is the background from that. And can you continue? And so the backbone of this system is a program called FFmpeg. I don't know if you knew that. So it's the basic component of stuff like Handbrake of Apple or a VLC player. And the structure of FFmpeg is command line based. So whatever you do, you don't have a fancy interface. Everything is command line. And it's really powerful. It's open source. And we compiled it back then with the Blackmagic capture cards and the NVIDIA cards, so that they can hardware encode the video streams in HD, which worked quite well, and then send it to RTSP servers. Can you continue? And this is then the structure, and I can really recommend it because, for example, with this simple line of code, you can, in theory, exchange audio from video file, which is normally you have to do it in Premiere and then re-render. With this little command, you can just swap the audio, for example. So it's quite powerful. And it's command line based. And you see here the underlying idea is that you have streams and like pipeline structure. So it's not like normal coding with like a certain syntax. So you build these pipelines. Okay. So, and what happened in the last couple of years, that NVIDIA used a similar code structure called GStreamer of Linux, and they rewrote it for their own purposes, which I think was quite interesting, so that they actually invested a lot of resources in rewriting GStreamer, and which is actually functioning basically like FFmpeg, so you have this streamline-based structure. And what they build them, so you have this input devices here that could be sensors or cameras. You have then a capturing, a coding device, or basically a block of coding. Then a pre-processing unit. This is all running on this GPUs. And then this is the new part, the interesting part, an AI inference method. So that means you can directly hook interference like classification and so on up with this video that you just get from the camera. So everything is happening on the board, right? You can also apply tracking. So you see the boxes around that. And then this is quite, I would say, the groundbreaking thing. You can connect it with message brokers. That means I don't need to send the whole data or the whole video to a central server. It's enough that I send data. So I can implement a JSON script that's connected to a server, and I just send them the classification data from these devices. So I save a lot of bandwidth. And these servers are then also centralized. So. And I also can hook that up with systems here, robot systems, and so on, and visualizations. So this is the idea. There's a visualization process at the end. So that means I think that the groundbreaking idea or relevant idea here is that the AI thing is not happening on a centralized server or as like a Skynet system, as like a centralized brain. It's actually happening on the edges. And this is where they invest a lot of money, and I think where the journey is going at the moment. So you have centralized servers that run the training, which is quite expensive and not available for normal people anymore. But the models you can deploy here. And after the models are trained, you cannot access them anymore anyways. So the training process is encapsulated from the actually inference process. This is quite necessary to know, I guess. Okay. So and around that, which is around a GStreamer, which is command line based, as said, they built this kind of structure, which is called a composer. Reminds a bit on software like Touch Designer and so on. And so you can build your own pipelines, which can get quite complicated, and build Docker containers. So that means you can build a certain program structure and deploy that on these devices. And on every device you have, it's the same structure. So you can say, okay, I make a Docker container out of that. And it's a bit like a compressed system, I would say, and deployed it on these small systems, and they run everywhere the same. So it's a highly industrialized division of labor process, where AI is just one part inside, right? Okay. And now I want to go a bit into the detail of my setup. So this is the code structure. So this is the code for the Blackfly for the cameras, right? So I get the cameras, the IP address, I capture them as raw data, and then I make something it's called muxing. So you don't need it for one camera, but for 4 cameras you need it. So you glue them together to one stream. And this is here the interesting command for machine learning. So you give the pipeline a certain configuration file, which is this here, and then the configuration machine learning model is loaded into the memory of this device, and then the inference, the classification of the video streams is done on this device. And you see, I think it's quite interesting that this structure is really. Yeah, it's more like a stream. It's not like a normal code structure. And you always refer to another layer of depth. So this is the configuration file for the machine learning model. And the machine learning model, again, is different. So and it's also closed. So you download that, so you use it. In theory, it's possible to do that yourself, but then you will probably need 1 billion or something like that. So it's super expensive to train. And you can define parameters here. And what you see down here, this is quite interesting. So this defines the threshold. This is the minimum threshold level that it's getting classified. And this is then the on-screen display and a render. So next, please. And this is the whole structure for the Orin setup. This was just an example. So this is the cameras again. This is the muxing. This is the detector. And you can also run secondary detectors. For example, when you want to detect cars. So you have one primary detector for automobiles, and the secondary detector will then detect which kind of car model you have, which also works quite well. And then you have the tracker for the bounding boxes, and then this is sending to the stream to a server. So I can grab it. For example, I use Touch Designer to grab the whole stream and reuse it, or I also can put the configure, so the classification data into a file, like here. Okay. And this would be the code at the end. So, okay, so yeah, we can skip that. So the structure of Deepstream is the base for two big projects, or two big packages of NVIDIA. One is called Fleet Command. So what you can do with Fleet Command is control up to, I don't know, millions of these small devices over a central server. So it's oriented on DevOps structures of modern IT. So you can develop a certain project and then build a Docker container, as said before, and then deploy it to the small devices and large. So we really talk about thousands of devices with one infrastructure. So this can be done by one person then. So you have a structure of deployment. You have deployment servers, and these servers are deploying then to the little devices on the perimeter, so to say. And you see you can really build network infrastructures like transportation, manufacturing, warehouse, retail, and healthcare. So obviously it's really aiming on infrastructure and logistics. And you can also access all the devices from the central server then. This is also possible. So you can log in and all devices, control every stream, and update all of them. Next, please. So the next big thing Deepstream is used is called Metropolis. This is for smart cities. It's also, it's quite obvious, I think, from the picture here. So it's for traffic and so on, but also, of course, for surveillance. Okay. So this is the application. So in theory, you can build a network structure, where you can surveil everything from production to manufacturing to retail. And here you see a system that is basically using 3D tracking for customer tracing. And next one. And here, this is for manufacturing. Right. Okay. So, and it doesn't work at the video. So the new iteration of NVIDIA Deepstream and of the classification systems are not really pre-trained, but you can define the classification on the fly. So for example, you have a stream now, then you can say I want to have a face, then it's classifying the face. I want to have a face and the left eye, then it's classifying the left eye and or the right shoe. So it's classification on the fly. And it's also working on this small devices. So the next thing I integrated was the robot. It was a bit quite an issue to get it. They were sending it on the wrong address, so I got it quite late. And so this is a model from Elephant Robotics. The problem with these robots was it's either really large, like you have industrial robots from KUKA and so on, and they're quite also dangerous and so on, and or you have toy robots, and there's not much in the middle that is also affordable. So they start normally at the price level of 20,000 euros. And this one is not so expensive. It's from Elephant Robotics. And interestingly, it also has an NVIDIA Nano here as a steering device. And what they do, which is also quite nice, that they level the control mechanisms on a certain edge. So it's like quite easy to use. They have a Python enrollment, but you can also use this arrow S here, which is also based on some kind of network structure at the end. I didn't get into that too much because it's obviously also really deep. Okay. And so what I experienced from all that is that the difference between hardware, software, and infrastructure are blurring more and more. And also that you enter a realm of, I would say, industrial division of labor. So you see really how this stuff is built, is for certain groups working on that, and everything is deployable and so on. And I think to really understand machine learning nowadays, you need to get quite a lot into the details of stuff of this new network structures in IT, like Kubernetes and so on, because it's really just one part of it. And also that a manufacturer like NVIDIA is getting it's basically like a monopoly. And they managed to develop things like this Deepstreams, but also like CUDA or QDNN, which is really on the hardware. So it's not just like the hardware you can use, you need to have their software packages, you need to use their software libraries and so on, and there's no way around. And so they're blurring this kind of borderline between hard and software. And at the moment, there is no other manufacturer for these graphics cards. And I think that could be quite, or can be quite problematic in the future. And yeah, so that was my experience. I see it a bit as a research project, but also as an art research project where I see myself involved in this developing processes, and I try to reflect a bit on it. Okay. And what I find interesting, I see similarities to the ideas of Gilbert Simondon. He was writing a lot about the technical objects. He wrote this text in the 50s, and he was a trained engineer, so he was referring to mechanical objects. And so, sorry, this is in German, but I can explain it a bit. So he sees technical objects has two tendencies in general. So one is caused by the auto-physical reality. That means when you have a combustion engine, you need to obey the physical laws because, obviously they cannot produce inside a combustion chamber too much pressure, otherwise it will explode and so on. But also there is an inner tendency to overdetermination. So that means one part is becoming more and more multifunctional. So at the end, this internal multifunctional parts disintegrate and became a whole new part. I think the best example for that would be a transistor. So, so I think this is quite a resemblance to what is happening in these processes. I don't think it's a really process I know from programming. I see it more of, it feels a bit more like it's mechanical. You know what I mean? So it's really like it feels like real machines. So at the end, it's not an abstract phenomena like formulas, like abstract mathematics. You really have something that is working in a certain way and is highly functional, and you combine it in a certain machinic way. Again, I think, I can just scratch that now, but yeah. So the whole project in general then is for me, I said, like a research, and I think this idea here of Bertrand Russell is quite nice. I can really recommend the study of mathematics. It's a text from 1910, And he talks about the idea what mathematics is about, or why you actually learn mathematics. And I would also see this as a reference to engineering or programming. So you don't learn programming or get interested into programming, in my opinion, because you want to do a product. Right? You can, of course, but this is not the main aim. But in the idea of mathematics, or in this engineering way of thinking, there lies a pure idea of humanity. So you can, no matter where you're born, or if you're poor or rich, you can learn mathematics, and with the basic knowledge of mathematics, you can contribute to this system, or you can also come into contact with all people over the world, and so it makes people equal. So for Bertrand Russell, mathematics was a kind of philosophy, I would say. It's a philosophy, but a humanitic kind of endeavor, which I think also is for me valid to these structures I just show you. So it's a certain way of thinking. It's very clear. And so especially when we talk nowadays about machine learning and arts and all these generative methods, I think in these constructions of these machines and a lot of algorithms is a beauty itself. So for me, like a system like a GAN or structures like that are more beautiful than the actual outcome that is produced with them. So, and I think it's also quite important that we keep on teaching and learning these things, not just because we have products, because I think they are beautiful. Okay. And now what the purpose or the general practical relation of that is to art projects. I can show you here. This is a work by David Halbrook. I did the whole technical background. So the really nice thing with these devices is, of course, that you can everything run on board. So you don't need a connection to a server. You don't need an API. For example, when you do a lot of stuff with machine learning nowadays, people use APIs. So that means that your art piece must be connected to a server all time, which can be problematic. So this is called Nachtal. Maybe David can tell you later about it a bit. So this is a sculpture placed in nature. That means we cannot place it in some kind of environment with internet connection and so on. And it's also cycling in a way, so it needs to be stable. And what you can do with these devices, and especially Linux, you can execute programs on a clock. So this here on the left is basically like a timeline and a clock device, and then it's triggering Python scripts at the end. And it turned out really well, I think, and it is quite stable. So, and NVIDIA is developing them further, and their aim is, especially when it comes to digital sovereignty, that this can save you from connections to servers in America and so on. And in theory, in the future, you could also deploy large language models on these devices and use them, which I think is quite interesting. So there's also upside to that. Okay, and so this is basically more actual project, also more infrastructural. So you can use certain infrastructures you already have, web-based, like we also have in this with VLAN atelier here, which is becoming more and more common. That you run cameras over net streams, that you run audio over net streams and integrate the systems, for example, for building tracking devices. So when you want to have 3D trackers, you can also use machine learning applications for audio to text and so on, and also building blockwise in infrastructures. And also upscale videos, improve the quality of videos, and so on. So everything is getting more network-based and decentralized. I think this is also a point. So, okay. Any questions so far?
I would have many questions, but perhaps not now. I don't know what is to follow.
Are you finished? Or?
Yeah, I'm finished now. So I have one slide, but maybe we can give this as a Zugang. Or maybe we can do this. Okay. You know it already. So so now it's in German, and I think Heidegger, whatever. It's of course problematic, but so Heidegger wrote in his text, I think it was in the 50s, about logic and about the way logic changes from logical thinking, mathematical structures, to an infrastructural way of thinking. And so that you have more logistics, and I think this is taking place right now in a certain way, that it's more about management of streams and infrastructures and so on, and also in the old military sense of the word logistics, which I think can be quite problematic in a way. And yeah. So okay, you can switch back to.
So you mean that we are living in a kind of time where the logic is more and more becoming logistics?
Yeah. So that's what he